So in this video I'm going to focus on the cylinder case. So basically this is the turbulent wake generated by a smooth cylinder. So I already have installed Xcompact3d and compiled the code, and for the post-processing I'm just going to git clone Py for Xcompact3d, which is our Python framework for post-processing of statistics. So and then you go in the directory and you just do pip install dot, and that will prepare this Python framework that we are going to use in a moment for the post-processing of the simulation. So I am going in the Xcompact3d directory example cylinder section, and I'm going to use the input DNS300 LR for low resolution. The important parameters for this simulation, so once again I'm using the default setup, the mesh node 257.128.32, the domain normalized by the diameter of the cylinder, 20 diameter by 12 diameter by 6 diameter, inflow outflow boundary condition in the streamwise direction and periodic boundary condition in the other direction. The Reynolds is 300. The incoming velocity is a uniform profile equal to 1. There is a little bit of random noise to trigger turbulence. We are going to do 60,000 time step, and we are going to use an immersed boundary method for the cylinder. I'm not going to discuss the immersed boundary method in this video. I suggest you have a read at our latest paper on immersed boundary method that is called a simple and scalable immersed boundary method for high fidelity simulation of fixed and moving objects on a Cartesian mesh. Basically, you have three options for this IBM parameter. If it's 0, there is no immersed boundary method. If it's equal to 1, it's the immersed boundary method without any reconstruction. If it's equal to 2, it's an immersed boundary method with Lagrange polynomial reconstruction inside the immersed object. And if it is equal to 3, this is cubic spline reconstruction, which are actually presented in this recent paper. So here for this example we are going to stick to what it is now, so flow reconstruction using Lagrange polynomial. We are using Adam Bashford 3 time advancement, saving the snapshots every 10,000 time step, and collecting the statistics after 10,000 time step. The location of the cylinder, there's an IBM stuff section in the input file, so CEX, CEY, this is the location of the cylinder, and I suggest you do not touch the other parameters. The one that is of interest is I forces, which will compute the lift and drag. It is set to 1 here, so we are going to compute the lift and drag. And in order to do that, we need to define a volume control over which we are going to look at the fluxes, and we'll extract the lift and drag calculation. So here our volume control is centered around the cylinder, obviously. So these are the parameters of interest. Changing the volume control dimension will not affect the lift and drag calculation, but in order to reduce cost, it's better to use a volume control that is as small as possible. If you want to deactivate the calculation of the lift and drag, you just put I force equal to 0 here. So as usual, I ran the simulation a little bit before, but I just want to show you that the simulation should run very quickly, probably in about 2 hours on my workstation using 16 cores. So this simulation corresponds to figure 4 of the software Xcompact3d paper. Okay, this figure 4 here, the bottom one, where we are looking at the mean velocity and the RMS streamwise velocity component at different downstream location in the wake of the cylinder, and the reference data are provided by Mittal Palashandar. Okay, so this and the data are available in the Pi4 Xcompact3d directory. I will show you how to do that. So the first thing we are going to do, we are going to focus on 3 things: the snapshots, the lift and drag, time evolution, and the statistics. So we are going to start with Paraview, and we are going to go in the data directory. Sorry, it is a little bit slow today. So we go in the example cylinder directory. If my I need to go back. Example cylinder. So in the data directory, so for me it's going to be in data fixed because I ran the simulation before. And you load the snapshot files with the XTMF reader. And I'm going to look at the vorticity, the magnitude of the vorticity, and I'm going to color it with UX. And this is typically what you will get. So you get your elongated span-wise large vortices, and you have these elongated streamwise vortices. So this is typically Reynolds number 300 wake, and at low resolution. And you can move on with the different snapshots that have been saved. So for the snapshots, nothing really important. Now you will see that you will have some forces.dat file. So I'm just going to open GNU-plot, and I'm going to plot the lift and drag. So you just need to read. This is a very simple file. Sorry, with 3 columns. The first is time, and the second is lift, and the third one is the drag. So if we look at this, this is the lift and drag evolution. The drag in purple, the lift, of course, centered around 0 in green. If we want to do a zoom in, so we're going to pick a small adimensional time between 250 and 260, let's say. This is what you will get. So the lift in green is oscillating around 0, and the drag coefficient is oscillating around 1.5. This is a slightly high value, but remember that we are at marginal resolution, so the calculation of the lift and drag in particular will not be very accurate. If you want a better estimate of the drag, you will have to increase the resolution of the simulation. The one last thing we want to do is we want to generate the statistics. So once again, we are going to go in our Pi4 Xcompact3d framework. There is an example directory in the cylinder, directory. As I said before, I'm using the parameters by default, but if you change the input file in the simulation, you will have to change the input file in Pi4 Xcompact3d. So the JSON file just needs to upload the correct number of mesh node and domain size. That's the only thing you need to do. And then there's this cylinder Python file where you just need to specify at what time you are stopping the simulation and you are looking at the statistics. So the one last thing I have to do is copy the mean file for the statistics. So they are in the statistics directory of the cylinder. So in my case, they are going to be in the statistics fixed. And we are interested in the last one. So we want to copy the 60,000 files. And then you just launch Python with the cylinder file. And you will produce two PNG files correspond to the mean velocity. So the agreement is good, not perfect with the reference data, but once again, we are at marginal resolution. And these are the various profile, various downstream location for U prime. You can see there is a fairly good agreement with the reference data. As usual, if you have your own reference data or if you want to make any change, please feel free to modify the cylinder file depending on what you want to plot, but at least I've showed you how to produce some basic statistics. The one last thing I want to discuss here in this video is if you want to, instead of simulating a cylinder, you want to simulate something different like a sphere or a square. You can do that by simply changing the geometry definition. So you go in the BC cylinder file, which is focusing on the cylinder test case, and you have this subroutine geom complex cylinder, where here you're basically defining this epsilon parameter. So epsilon parameter is a parameter that is either equal to 1 or 0. It's equal to 1 in the immersed solid object and 0 in the fluid. And basically here we're just saying that if a mesh node is within this circle, the epsilon parameter is equal to 0. Okay, so here if you change these equations, you can put an airfoil, an ACA equation, you can put a square equation, but this is how to do it. Then the code will take care of everything else in terms of preparing for the reconstruction of the velocity inside the immersed object.